Module 11, Introduction. Basic Lewis diagrams. Lewis diagrams depict the bonding between atoms in a molecule or molecular ion and also show lone pairs of electrons. They can be used to predict molecular shape. By following the 5 steps provided in this module, you should be able to construct basic Lewis diagrams for a number of molecular species. More advanced topics related to the construction of Lewis diagrams will be covered in subsequent modules. Step 1. We need to find the total number of valence electrons available for a given molecular species. And here we will go to the periodic table. Hydrogen is in group 1. There are 2 of those. Oxygen is in group 6. We have a total of 8 valence electrons to use in the construction of the Lewis diagram for water. Carbon is in group 4. 4 of those hydrogens each in group 1. Again, a total of 8 valence electrons. Sulfur is in group 6. Fluorine, a halogen, is in group 7. We have a total of 34 valence electrons available for sulfur tetrafluoride. Next, we need to identify the central atom. Now, for more complicated molecular species, there may be multiple central atoms associated with that particular molecule. Here we're going to keep it relatively simple. We'll try to abide by these rules that central atom is never going to be hydrogen. When given a choice, it will usually be the least electronegative element. There are certainly exceptions to that particular rule. Eventually, your chemical intuition will enable you to best identify central atoms. Nature does tend to like symmetry. So here, given the choice between hydrogen and oxygen, knowing it can never be hydrogen, central atom there would be oxygen. Here the central atom, carbon. Fluorine, the most electronegative element on the periodic table. Wouldn't expect it to be a central atom. We'll go with sulfur. We've identified the central atoms. We're ready to move on to step 3. We want to connect the central atoms to the outer atoms using chemical bonds. So I'm going to use a line to represent that chemical bond. That line also represents 2 valence electrons. So here I'm just going to connect central atom to outer atoms using initially just single chemical bonds. Sulfur, fluorine, 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 and fluorine. Notice I'm not trying at this stage to convey what the actual 3-dimensional molecular shape is. I'm just constructing a Lewis diagram that can be used as a tool in conjunction with other information to determine what that actual 3-dimensional shape would be. Okay, so I've got the connectivity. Now I need to complete octets as necessary. So the most stable configuration of these atoms tend to be ones in which the elements see or have a share in 8 valence electrons. Right? There are notable exceptions to this rule as well. Hydrogen is plenty stable, having a share in just 2 valence electrons. Covalent compounds of beryllium, 4 valence electrons. Covalent compounds of boron would have 6 valence electrons. And then for elements in period 3 on the periodic table and below, so here we're talking about elements in this period and below, they can have an expanded octet, more than 8 valence electrons. Okay, so let's complete the octets as necessary. We had oxygen, hydrogen, hydrogen. I need to give the oxygen its octet. I'm going to do that by introducing lone pairs around that central oxygen. From the standpoint of the hydrogen, it is seeing 2 valence electrons. That hydrogen sees 2 valence electrons. The central oxygen is seeing a total of 8, 4 in those bonds, another 4 in the lone pairs of electrons. Carbon, hydrogen, each of the 4 hydrogens. Again, each of the hydrogens has its duet, and from the standpoint of that central carbon atom, it already has its octet, 2, 4, 6, 8 valence electrons. Sulfur, fluorine, fluorine. Here, those outer fluorine atoms need to have their complement of 8 valence electrons. So I give each of those fluorines 8 valence electrons. From the standpoint of each fluorine, there are 6 electrons in the 3 electron pairs, plus another 2 associated with that bond line. Each of the fluorines is seeing 8 valence electrons. I now am ready to go to step 5 to check the number of valence electrons used to the number that were available. Okay, recall back in step 1, we had 8 valence electrons associated with water. In giving everything its octet or necessary duet, I indeed have used 8 valence electrons. That tells me this is an acceptable Lewis diagram associated with water. Same is true for methane. I had 8 valence electrons. I used 8. Everything has its octet or duet. This is an acceptable Lewis diagram for methane. For sulfur tetrafluoride, I have used 32 valence electrons at this stage, but I had 34 available. I need to use the entirety of those 34 valence electrons. Every time this case arises, I construct a Lewis diagram. I've abided by the octet rule, but I haven't used the required number of valence electrons. I will continue to add lone pairs to the central element until I've used that required number. By adding another lone pair to the sulfur, I'm now using 34 valence electrons. Let's try a couple of additional examples here. Let's try one where I don't really have a central atom. Let's try a diatomic molecular ion. How about cyanide? So carbon is in group 4 on the periodic table. Nitrogen is in group 5. And I need one more electron in order to impart that -1 monovalent charge to the anion. That's going to give me a total of 10 valence electrons. Okay, so step 1, we've identified our number of valence electrons. Here, there really is no central atom, but I will connect them, the carbon to the nitrogen. I'll give everything an octet that needs an octet. I will check the number of valence electrons that I've used. Let's see here, I've got a total of 8 around that carbon. There's 10, 12, 14 valence electrons used. I only had 10 available. Okay, every time this case arises, I will need to take a lone pair of electrons away from a central atom and, given a choice, the least electronegative of the adjacent atoms, and introduce a multiple bond between the two. Here I'll take a lone pair away from nitrogen, a lone pair away from carbon. I introduce a double bond. Now I'm still abiding by the octet rule from the standpoint of each of the 2 atoms, but I'm using 2 fewer valence electrons in coming up with that structure. Even though I'm using 2 fewer, I'm still using 2 too many. 8, 10, 12 valence electrons utilized. I only had 10 available. I'll do the same thing again. I'll take a lone pair off of the carbon, a lone pair off of the nitrogen, and again I'll introduce another bond line between the atoms. Now from the standpoint of the carbon, it has its octet. Standpoint of the nitrogen, again it has its octet, but in the entirety of this molecular ion, this Lewis diagram, I am using only 10 valence electrons. I also want to indicate within my diagram that this species carries a -1 charge. This is the Lewis diagram for cyanide. Let's do one more. Let's try sulfur dichloride. Again, step 1, we need to identify the number of valence electrons. Sulfur is in group 6. We have 2 halogens from group 7. We have a total of 20 valence electrons. Central atom, we'll go with sulfur, less electronegative than chlorine. It's also going to impart more symmetry to my structure. I'll attach those adjacent or outer elements. I'll give everything an octet that needs an octet. Here, that is everything. So all 3 atoms now have the required octet. I count up how many total valence electrons I've used. Well, there's 8 around that chlorine, 8 around that chlorine. That is 16, 18, 20. I've used 20 valence electrons. I have a stable structure from the standpoint of abiding by the octet rule. I had 20 valence electrons available. This is the Lewis diagram for sulfur dichloride. So master the construction of basic Lewis diagrams by completing the exercises associated with Module 11.